So let's get started. We're going to run a quantum sensing quantum marketplace today, and we have 4 companies that are going to partake in this. We have Castor Optics, SBQuantum, Northrop Grumman, and AOSense, and I'll introduce the speakers later once we get into this. So I'll give some updates on the quantum marketplace, quick overview and trends in the space, and then we'll get into the lineup. We'll get into the lineup, and then we'll have a roundtable discussion. Okay, so what is the quantum marketplace? It raises brand awareness, facilitates collaboration, deals, and partnerships. So we have both a web directory on the left, which is on the QED-C homepage, which lists all the member companies, and there's a little pink icon next to their name if they've presented in one of these sessions before, so you can learn more about what they're doing. Also, if you click on their name, you can get a description if they've filled that out. And then also, after we do these events, we post the recordings on YouTube. There's a lot of content here, a lot of learning you can have in a specific segment, be it the supply chain, be it quantum networking, sensing, your quantum business, even legal and export controls. We've done things like that, quantum computing, et cetera. So today, again, these are the 4 companies. Again, you can go to YouTube/Quantum Marketplace, and you will see this recording posted usually in about 2 to 4 weeks after the time of the event. So in terms of what's going on in the space, I like to pull this market research from last year from McKinsey, which covers computing, networking, and sensing. I break out timing from that, which is part of sensing. Today, mainly, we're going to essentially talk about timing and sensing, which you could call quantum sensing. Fairly big market size. Doug, you showed some of that material earlier today. What I want to talk about here is sort of just a general sense of, this is not an exhaustive list. You're going to hear much more from the presenters about what exactly they're doing in the space, but Mike has a magnetometer. Put it up, Mike. He has a fictitious magnetometer that he has a real thing back home, but he brought it with him here. Camille has brought a live NV Diamond Center magnetometer for people to play with right in front of the stage here. So after the session, we can come play with that. Another area in terms of electric field sensing, RF antennas. This is a big area. You hear the term Rydberg. There's some QED-C sessions right now also going on, as Celia talked about, to educate people. What are the details? How does this work? Also, we've heard a lot about inertial sensors. Brent's going to talk quite a bit about what he's doing there. I know Mike's working in that area as well. And this covers the spectrum, from accelerometers to gyroscopes. We're always hearing about GNSS-denied environments. This is a way to deal with that. There's gravimeters, gradiometers, there's relativistic geodesy to detect earthquakes, and there's also consumer markets down the road. And then there's another thing that's, and this is why I sort of break timing out, is optical clocks are coming. Many companies are now building units and deploying them in the field, and they are going to start replacing the RF-based atomic clocks. So where do the companies sort of fit most? I'm not expecting this to be perfectly accurate, but Castor Optics is more in the supply chain side of the equation, versus Northrop Grumman, AOSense, and SBQuantum are actually providing solutions to their customers in terms of a full system. So today, we have Mike Larson from Northrop Grumman, we have Brenton Young from AOSense, Kathy Bedette from Castor Optics, Camille Georges from SBQuantum, and with that, Mike, you come to the stage.
Thank you, Mark. Well, good morning, everyone. My name is Michael Larson from Northrop Grumman. I'm the quantum science architect in our emerging capabilities development organization within the mission systems sector. This is the kind of slide that just about everyone at some point who's doing quantum sensing has put together that says, oh, well, why are we doing quantum sensing? Well, because atoms and photons in the quantum systems we're going to use, they're They're identical. You can make them isolated. They're easily manufacturable because nature does it for you. They're unbreakable. They're going to push the boundaries of sensitivity and performance. And that's great. This is why science and engineering and the technical folks would love to go work on quantum. But this isn't why Northrop Grumman's primary customer, the DoD, is interested in quantum. What they want, and this is echoed in the sentiment from Heidi Shu recently in her statement, they want leap ahead capability. They want to compete with their adversaries and have an advantage. That's what they want. And if they can get it from quantum, then they want quantum. If they can get it somewhere else, then that's what they want. But what they really want is leap ahead capabilities. And they want it rugged, and they want it fieldable, and they want it to make missions possible that they can't do today, or make them possible to do better than they can do today. Over the many years, quantum technologies have driven radical advancements in technology, and that's what the DoD is leveraging on, is saying this next generation is going to do similar things. And this is not the right slide deck, but that's okay. This is the old one. So within Northrop Grumman in quantum sensing, we focus on 5 main areas, which are sort of the 5 traditional areas that atoms are good at being sensors. And that's oscillators and clocks, magnetometers, RF receivers, accelerometers, which of course you do gravity or gravity gradient. It's all just an accelerometer, and gyroscopes. There are offshoots. Everything's a thermal sensor, but or a vibration sensor. And with these, our focus is making them rugged, fieldable, and support new missions. Thank you.
Thank you. There you go. Yep. Brent.
Brent Young from AOSense. Thanks so much for the opportunity to describe AOSense capabilities in quantum sensing, atomic clocks, and atomic clocks and enabling technologies. Quantum sensing and clocks are really poised to dramatically improve capabilities in defense, national security, and commercial applications. AOSense has a broad range of different applications that it targets. However, our prime mission has been to develop or improve navigation timekeeping for GPS-denied environments. As far as navigation is concerned, the ultimate performance that we anticipate for atoms would be to achieve navigation and accuracies less than 5 meters after about 24-hour of navigation time. Typical aircraft navigator drifts about half a nautical mile after an hour. So this represents about a 200 times reduction of the error for a longer time period. In terms of atomic clocks, right now they're the best clocks in the world perform much better than the nanosecond per year that we're quoting right here, but those are inappropriate for fielded missions. And so AOSense's objective is to be able to deliver atomic clocks that will perform at this level in moving platforms. Actually, back up here. If you look at classical sensing technologies, like the best conventional accelerometers and gyroscopes, they're vastly different technologies. One of the strengths and appealing features of quantum sensing is their commonality. Because of that commonality, a small company with a modest staff, or staff about 35 at AOSense, has really been able to achieve significant advances and demonstrations in a broad range of different sensing modalities, as indicated there. The green checks indicate that we've developed a laboratory prototype and demonstrated it, and the gold stars indicate that we've demonstrated it either in a field or an external testing laboratory. When AOSense first started in 2004 developing quantum sensing, there was very little in the way of enabling technology suitable for fielded systems there, which really motivated AOSense to develop some of our own, leading then to the next slide, which shows some photographs of some AOSense enabling technologies in photonics and vacuum and electronics. For example, our laser diodes and our laser driver electronics deliver ultra high performance at low size, weight, and power or swap. And premier research groups around the world purchase our high brightness atom beam systems to accelerate their quantum research, enabling them really to focus on the physics rather than focus on engineering atom sources. The quantum gyros will soon be revolutionizing GPS-denied navigation. In 2021, the DARPA approved public release of AOSense results from 2009 on quantum gyros that really achieved outstanding noise and bias performance. You need to wait for about 1 hour for this gyroscope to drift off by 1/1,000,000th of 1 degree, which is really extraordinary stability. And subsequent research at AOSense has been focusing on taking that type of technology and being able to transition it to operate under motional dynamics, and also to be able to combine single axis sensors together into what you describe as being a 6-degree of freedom quantum inertial measurement unit, or QED-C. And so recent advances in this area, in 2023, Boeing announced a collaboration with AOSense in which we demonstrated the world's first 6-degree of freedom quantum IMU on a ground vehicle. So that's some information on that depicted there, in the lower left. And then this year, we continued on and we demonstrated the world's first quantum IMU on an air platform. So again, that's 6-degree of freedom, 3-axis accelerometer, 3-axis gyro, all of them quantum. And so, given sufficient funding, our goal is that around the year 2030 that we will be able to field an engineering prototype for a quantum IMU that will reduce the current volume from about 100 liters down to about 6 liters. The current version that we're doing the testing on is basically taking 3 separate single-axis sensors, combine them all together, and so then this will be something engineered for an integrated system. So in terms of absolute gravimeters and gravity gradiometers are very useful for national security, for precision navigation, and for geophysical exploration, very useful tools. And so this table here, and AOSense delivered in 2010, about 14 years ago, the world's very first portable quantum atomic gravimeters, this single axis device. And this table summarizes and compares existing technologies for absolute gravimetry against AOSense target of what we want to put into production around the year 2025. And what it shows is that our goal will be to deliver much better sensitivity in a drastically smaller package. The key thing to compare there is the 1,500 liters, 40 liters, and 20 liters. And so what's depicted there in the lower left is a less than 20-liter container that includes the entire system, whereas the conventional systems all have kind of a separate electronics unit and the sensor head. In this case, all the hardware is integrated into that one unit. If you have an interest in assessing the capability of quantum sensors or advanced clocks to improve your applications, or if you have an interest in accelerating research using components, please contact us. Thanks.
Thank you. Good morning, everybody. So today I will present you Castor Optics. So at Castor Optics, we manufacture and develop specialized low-loss fiber optics component for application when every photon counts. So I'm Kathy Baudet, and I'm its Business Development Director. So what do we do? So our technologies is based around the same core technology, which is a fusion and tapering of fiber optics. Using specialized fibers and proprietary processes, all our products aim to increase the signal-to-noise ratio of a sensitivity system, which, as you know, is very critical, especially for systems with very low photon count. So we develop a range of enabling technologies for the next generation of photonic sensors. And because of their high performances and low noise, these are ideal for the quantum sector as they operate in low light or high noise conditions. So we've pushed these technologies already in various markets, including biomedical instrumentation, LiDAR, or sensing in the general term. And pushing those technologies into these markets have allowed us to develop turnkey systems or upgraded solutions that not only optimize the efficiency of the system, but also reduce noise contributions. So we work closely with our customers, starting either in the academic lab directly or with R&D teams in industrial setting to develop dedicated solution for their specific application. And we follow their progress all the way to industrial production. So we currently have in our portfolio more than 10 customer-driven R&D projects. Some of them have reached the production phase. So we offer a lineup of various products that can be used for different photonic modalities or implementation. So based on our processes, state-of-the-art processes, all our products feature very low losses. And also we can offer them in compact packaging for seamless integration or again for use in cryogenic conditions. So while we have several products that are already in market, we are always continuously pushing the technology further and developing our capabilities. So for example, we don't have any pointers here. Oh, yes. Oh, it doesn't write on the screen. Anyways, we're developing specialized structures and multi-fiber couplers, which you can see in the corner. They're pretty gorgeous here. That can be used for various sensing modalities. So we can tailor those geometries for specific applications. So our objectives is to seek partners and collaborators to validate our technology in the quantum sector or to explore new opportunities for developments. So for example, we're developing a line of mode converters to be able to solve fiber connectivity challenges, either for quantum detectors such as SNSPDs or for quantum computers. We're also developing monolithic optical hybrids, very low loss, again, for quadrature detection. And we also offer various multimode circulators or couplers for sensing modalities such as NV center-based quantum sensing. So we're looking for system integrators in the field of quantum sensing, for laser or detector developers, or again, for quantum communication. So I would like to thank you for your attention, and I'm looking forward to hearing about your fiber optics challenges and how we can help you. Thank you.
Good morning. Thank you again for the opportunity to present today. I'm Camille. I'm the Director of Operations of SBQuantum. We are based in Sherbrooke, Quebec, in the heart of the Quantum Innovation Zone. And I'm here today with my colleague, Adrian. And as Mark said, we have a very nice demo here today with our device. So come and have a look later today. At SBQuantum, we are developing next generation magnetism, magnetometry based on NV centers in diamond. On the very left of the slide, you can see a diamond lattice. When a diamond is pure, it's going to be composed only of carbon atoms. But here we are very interested on one specific impurity in diamond that's called an NV center, which means having a nitrogen and a vacancy, neighboring vacancy, instead of having two neighboring carbon atoms. To measure the magnetic field, we shine a laser and microwaves to the diamond, and we retrieve the red light. And it is in this red light that we are able to retrieve the magnetic field measurements. So you can see on the right picture of the device, but it's always better in live. So you have it right here. And you can see a quick comparison of our technology versus different other techniques of magnetometry. But I want to point out the two main aspects. So first, our technology enables to do room temperature measurements, which is a very great advantage for integration. But also it is possible to measure not only the magnetic field intensity, but the magnetic field in value in each axis of space. At SBQuantum, we want to move beyond the magnetometer as a commodity game. So actually, we are not only developing the sensor itself, the magnetometer, but also ML compensation algorithms on the one side and data analysis and interpretation. So for compensation algorithms, they are essential to integrate the magnetometer into different platforms, as this platform will have a magnetic signature, and it's an issue, and it's considered as noise as we are measuring magnetic fields. So these algorithms enable to integrate our sensor into a satellite that will be launched into space next year in 2025, but also to integrate our sensor into a drone for different applications that I'm going to detail right after. Data analysis is also very important, as for the end user, the goal is to have they are not interested in having the raw data, but having like a full interpretation of like what it means for their specific use case and specific needs. So this technology has three main application domains. On one hand, mineral discovery, as so magnetometry has been used for decades for mineral discovery. So in order to detect mineral deposits on the field, thanks to a non-destructive technology, what we have developed at SBQuantum enables to have 9 times the magnetic maps compared to the classical solutions of the industry, making a difference for mining companies in the field. For navigation, so as I said, we will launch our technology into space next year, and that's part of a challenge called MagQuest, which goal is to refine the world magnetic model, which is actually the Earth magnetic field maps. So in this challenge, we were able to do extensive testing at NASA's facility in Washington. And finally, this technology is also can also be used to detect objects and to classify them. For example, for special forces, they are really interested to see when they enter a room, what is behind, if there are weapons, if they are moving. So this is something that's possible to see behind walls thanks to this technique. We are looking for different aspects of our technology. First, collaborators for R&D project to collaborate, but also, of course, pilot opportunities to go in the field and deploy our technology for all of the applications I've detailed earlier. And finally, of course, early adopters to test our technology. Thank you so much for listening, and thank you again, Mark.
Thanks, that was great. All right. So quantum sensing, including next-gen optical clocks, are considered by many to be closest in terms of commercializing quantum, actually getting it out there, quantum 2.0 in terms of the technology. So Mike, starting with you, how far away is your company's quantum sensing commercialization solutions? And I realize DoD is your customer, but how far away is it now?
Yeah, so it's an excellent question. And across the board, at the moment, I would say the two closest areas are the magnetometer and an atomic clock we're working on. In
And
those two
optical atomic clocks, right?
No.
No. Okay.
No.
All right.
Very, very tiny atomic clock.
Okay. Sure.
In terms of timing, what I will qualify this with is with the statement with sufficient funding, which is always the caveat you've got to put on everything. But with sufficient funding, I think both of those are less than 5 years from being able to be a product. And then on several of the others, when you talk about inertial sensors, one of the biggest challenges to saying, well, it's a product, it's being deployed, is the level of qualification that they have to go through before they're allowed out. So we may have sensors ready in 5 years, but it's going to be another several years or 5 years beyond that to get them fully qualified and in the field.
And that's because some of the operational environments on the platforms are extreme?
Yes.
Like, for example?
Well, okay, so first off, for most military platforms, there's, independent of how extreme the environment is, there's a lot of qualification that goes into getting a system approved to be on that platform from a safety and all the rest of the rigor that goes into DoD platforms. And then, if I was to think about the munitions application, for example, which most people in this room, if you were talking quantum inertial sensors, you'd say, well, that's not going to go on a munition. You can't survive that kind of environment. But we've started showing that for the right technologies, 30,000 Gs, okay, no problem. But
So
you
that's like,
have to,
that's like a launch or something, right?
yeah,
30,000 Gs.
yes.
Wow.
And that's the kind of ruggedization that you need to start getting into to make sensors reliable and robust for the DoD. Not every environment needs 30,000 Gs, but you've got to be dealing with vibration, shock, thermal, longevity. And that's another piece where, you know, the supply chain here is going to be so critical, is we have a lot of components where we can demonstrate the capability. We can even demonstrate it for months or a couple of years, but we don't have components yet with the longevity in terms of, you know, depending on what you pick in terms of lasers or in terms of other elements that you need in the system to get that 20+ year operational life that the DoD would like to see. And then the challenges also go up when you start talking about radiation environments. And it's that robustness of the technology that's a big part of the challenge right now.
And radiation is because of space or because you're dealing with something else?
I'll go with yes.
Yeah. So I want to, thanks, Mike. So I want to jump to Cami. So what you're showing us today on the table, that's not as far away because you're not targeting those types of environments initially, right?
So yes, what I'm showing right here is really our device. And going back to your first question, so we have sold, we did our first sale of a
So
device.
you made money.
Sorry?
You sold it. You
Yeah.
made, oh, wow.
Yes, so late 2023. But as I said, so we've been deploying the technology on the field for quite some years now. For example, doing pilots with mining companies, really to refine our technology, refine the features of our product to really match their specific needs on the field.
Great,
Thank you. Brent.
So our time frame for first products is about -14 years. The difference between what we do and what Mike does is that he's kind of looking largely at the next step of kind of production models that are going into the field. Whereas as a small company, AOSense is doing, starting with engineering prototypes that then we sell for evaluation purposes. And so it's, larger organizations then who are interested in potentially getting ahead of competitors and putting things into the field, who are interested in buying the engineering prototypes on an evaluation basis to decide what to do next. But then I agree with Mike that, for the actual production units, that takes another round of funding to push it out further. But right now, those one-off prototypes for engineering activities are there. You heard me talk about the, field demo, the ground demo and a flight demo, that's hardware. That's, some of it's even sold as commercial products.
Right. So would you say you take it up to TRL 6 or something, or how would you?
Yeah, 5 or 6 depends on the environment and the requirements.
And so what Mike was saying is that's the big money, 7, 8, 9, TRL 7, 8, 9. Yeah. Okay.
Yeah.
All right. Kathy.
Yes. So the question is a bit different for us. As you mentioned, we're a little deeper in the supply chain. So we do have commercial solutions. We have our couplers that are sold in different markets. But for the quantum sensing specifically, yes, we could commercialize products. But what we're really trying to achieve is to work very closely with the customers because the sensors are being developed as we speak. So we have to align our specification to their technical requirements. And that's what we're trying to do before we launch full line commercial products. So we could launch tomorrow, but I think there's a benefit to just working with pilot studies and beta users to first mature the technology and see what flavor will have the most traction for the community.
Great. Thank you. So quantum sensing system solutions require leading edge hardware components in many cases, right? In terms of performance, reliability, ruggedness, given various operational environments. So how are you addressing this early market build out? And we'll go back to Mike on this.
Thanks, Mark. So when we're in an R&D and development stage on any new technology, it's very important to keep in mind where you're headed. and that you want to get to production, and that you not take what at times is the tempting and easy path of saying, well, I'll partner with a national lab or another organization that's making some specific component that I'd like to have in my system, but instead saying, well, I'm going to invest a little bit more to work with either this small business or this other supplier who I know has a capability and a pathway towards production with the capability that I'm going to develop with them in partnership at the R&D stage. And so, you know, to that point, and somewhat in the vein of what the others have said, we have in that way developed vapor cells that are commercialized right now with some partners. We have developed lasers that are commercialized with partners. We are working on the development of PICs that will soon be commercialized through our partners on the component side. And yes, we of course have built engineering demonstration units that have either gone out in the field on, you know, land vehicles, ocean vehicles or air. Not yet in space, but it's those maturation steps and keeping them in mind at the early stages that helps to create the efficiencies you want in the development of the new technology, keeping the final product in mind.
Great, thank you. Brent?
Yeah, as I mentioned, you know, we from the very beginning, we've been working on defense contracts and you know, lifetime of operation and operation under motional dynamics has been and temperature range has been a key criteria, and there are a lot of components where that can be very challenging, but that is something we've been paying attention to along the way. You know, we have certain customers come to with certain requirements in those different areas, and so we wind up identifying components that may exist already, or else, as I said, we develop a lot of our own just because they were never there. Especially again, AOSense. We're you know, an old timer in quantum. We were founded in 2004. So we from that very beginning we started developing these compact, robust technical solutions.
So these even though you're doing systems, you're now starting to sell some of these components,
yes,
right, as well, that you've developed so your systems will work?
Yeah, it's a significant part of company revenue.
Okay,
Yeah.
great. Kathy?
Yes, that's a great question. And the way we've been addressing this market is really trying to preserve a certain agility to be able to respond to the ecosystem in terms of very high performance and reliability that you're looking for. But each application will require a different flavor, as I mentioned. But also in the meantime, having a pathway to high production, it's very important as well. And because we're in different markets, all our processes are up to the industry standard, and we have pathways for high production. So we're trying to follow those two paths of staying agile for R&D or custom orders, but also moving forward with our own industrializations as well.
Great, thank you. Kemi?
Yes, aligning to what the others already said. Yeah, agility is important, and for us, it really means like going to the field and understanding the market needs in all these different applications that we're looking at. And this is so important for us to adapt our solution to like the requirements that are expected. And also regarding components, so we are working with great suppliers and partners, which some of them are here today, and you know, in order to have to meet really this market expectations.
So I'm glad you brought up that last point, because so correct me if I'm wrong, but there is a lot of photonic and component suppliers in the Quebec area, right? Can you talk about that a bit?
Yeah, so actually, so as I said, we are developing a magnetometer that's based on NV centers in diamond. We are not growing diamonds ourselves. Like, this is the first component of our technology, like the base of it, and that's not something we grow ourselves. So we have great partnerships in order to get this diamond supply with companies that have a great expertise and provide us with great components.
Great, and this is, I just love this, right? Because I've never seen anybody put a NV Diamond Center live demo at an event like this. So I think this is the first time. Celia, have you ever seen one of these live? Maybe in a lab, right? So, okay. So Camille, Cami, I'm going to go back to you on this. What question are you hearing most from your customers today since you're taking orders and selling and shipping?
Yeah, I feel a question that customers have, and that's of course really makes sense, is like, why is it different, and why does it make a difference for my specific use case, for my specific requirements? How is it different from what I currently use, and what it can bring specifically for me. So that's what we refine with them, actually understanding specifically what they expect from this type of technology.
Great. Kathy?
So the question we're hearing most in different forms is, how can I increase my sensitivity? It could be, can you guys help me go from 0.3 dB insertion loss to 0.1 dB insertion loss? Could be, could you reach, instead of 33 dB return loss, could you reach 37? So we're in this fine tuning of getting the most sensitivity at each level of the components, a different aspect, to provide quantum applications, which is extremely sensitive, unless you do it on a table, but extremely sensitive and very low photon count. So you have to be able to collect all of these photon and bring them all the way to your detectors to be able to have the most sensitivity.
Great.
And the other question, is it possible? Yeah.
So sensitivity.
Yes.
And is it mainly on insertion loss or other parameters too that you hear?
Sorry, I didn't hear you.
Oh, is it mainly on insertion loss or is it also other parameters that you're hearing?
Insertion loss is the most because you want to have the highest throughput, highest efficiency. Return loss is also a great factor because you can have the most high level of signal you can, but if your noise is at the same level, you're not going to get anything. So increase signal, reduce noise, so insertion loss, return loss, and then the other factor is the form factor or packaging that is required for different mechanical or environmental conditions.
Great. Thank you. Brent?
Well, I might echo something that Mike said a little bit ago during his presentation, that if you're talking about DoD customers for GPS denied navigation, they don't care it's quantum unless it's dedicated quantum funds. They just want to say, what's going to do better than my existing sensors? And so what is the point? I mean,
So black box.
yeah.
Is it better than classical? Is it better than what I use
better
today?
than what they're using right now?
Yeah, right.
That's what they want to know. And one of the slides I showed was kind of a bubble chart comparing different gyroscopes. And if you think about the ring laser gyros and the fogs, which were performing worse in field applications than what we got on our original PINS gyro, but over $1 billion was invested into those technologies over about 50 years. And so, it takes a little bit of time to kind of bring something up as a new technology and to be able to catch up to the point where you can, do better than the existing technology. So that's the big question, is when can you do better than what they have right now?
Yeah, and I really like that you made that comment because it's something that's very evident in this community is we're staffed with a lot of technical people who really fall in love with the technology.
Mm-hmm.
But at the end of the day, a lot of the customers want something that just works better. They don't care what's inside.
Mm-hmm.
Right? Mike?
So there are 3 questions I want to highlight. One is the sort of common one that you already put out, which is I get asked, how soon will this be available? How soon can I have it to go deploy it? Number 2, which is a little bit of an odd one, but has kind of been echoed, is this really going to be real? Because in some cases, the revolutionary capability is one that said, well, I've always wanted that, but just assumed I couldn't have it ever. So I've worked around it. I've found other solutions. But if you tell me I can actually have it, well, then I want to know, show me how I can believe that's real, because it's hard for me to believe. But the third one is one that really this community needs to ask more, because we do a lot of technology comparisons between, well, where is quantum versus these classical technologies? And we fall victim to the same sort of thing that almost everyone else doing comparisons like that does, which is we pick a moment in time to compare to. And then we talk about our aspirations of where we will be when we're finished. And we don't say, where will those competing technologies be at that time? And we need to be projecting forward and saying, if I'm going to compare gyroscopes, for example, where will fogs be in the future? Because they are still investing and they are still developing. Where will MEMS accelerometers or some other traditional technology be in 5, 10 years? Because the other point of the DoD is if they can get the performance in a more robust package, in a cheaper package, in something they know and love and can rely on, they're more likely to go that way than to the unproven, not yet fully experienced quantum device that is the first one of its kind. And so there's
Yeah,
a larger challenge there.
Yeah, and there's also other aspects to that too, right? That you may have a much better mousetrap, so to speak, but a lot of aspects of the armed services don't like change.
Right.
They want to stay the same. So you have to have something super compelling, right?
And
You have to have advocates, right?
And every time you ask them to make a change, they'll ask you, how much will I save if
Yeah.
I make that change? You can't tell them, but I'm going to give you better.
Right.
And it'll be more expensive, but I'm going to give you this better. It's like, well, no, if I'm going to switch out what's on my platform, I have to invest to make that happen. And so they want to know how much it's going to be cheaper when they make that investment.
Great. Thanks for that extra color. So back to Cami, what is your company's biggest challenge in succeeding in Quantum 2.0 with this kind of solution and others?
That's a very interesting question. I feel I've mentioned that, but of course, in magnetometry, what's really important is that we are measuring magnetic fields, and magnetic fields are everywhere. So not only developing the sensor, but developing algorithms, noise compensation algorithms, to be able to deploy this technology, which is essential if we want to match and to answer the industry's needs. Specifically. So this is really something we've been working on, for example, with the satellite deployment and other type of deployment scenarios. For example, for the mining industry, we are currently working with a partner that is developing a gravimeter, and we are co-integrating both of our technologies into a drone to make a difference for the mining industry. These techniques are complementary in the end, and we'll give more information.
So how much does it weigh?
Oh, a few grams.
The whole sensor?
Yeah, this is the full sensor. So I cannot tell you the exact number, but like it's a few hundreds of grams.
Wow.
You can weigh it yourself afterwards.
Okay. All right. Thank you. Kathy.
I would say our biggest challenge is really to stay fresh in our innovation cycles all the time. So we have to push our technology further and to ideally be one step ahead of what the market is going to need in terms of components. So it's always hard to predict what's going to catch on and what the needs are going to be. But how we address that is, again, to really stay in close contact with our customer, with beta users, with academics labs as well, to really see what's coming and how we need to align our own innovation goals with them in terms of processes, not only the components themselves, but how we build them and how we build them reliably as well.
Great. Thank you, Brent.
The clear answer for AOSense is lack of sufficient R&D funds.
Yeah.
We're kind of a world-leading company in terms of quantum sensing, yet as far as I know, we have not gotten a single dollar of US NQI funds for any R&D work. We do sell a lot of commercial products to universities, but it's the universities in the US and the national labs that really control the funding for NQI. And we're even part of an NSF center, and we haven't gotten a dollar for R&D. We've proposed things for R&D, but they'd rather just use it in the academic environment rather than give to AOSense. So that's really been we're doing quite well on commercial products, but we could be moving a lot faster, but we're really limited by R&D funding for the sensors.
Are you familiar with DIU, right?
Yep.
Yeah.
I am.
Yeah. So that hopefully that helps with that.
Yep. Hopefully. Yep.
Yep.
We're pretty excited.
Yep. Mike.
So the way I look at this, focusing purely on DoD, is, yes, I can solve supply chain problems. I can solve manufacturing problems. I can build great sensors and great systems. But if I haven't connected the dots for the customer that says, this is the revolutionary capability you get because of it, and whether I'm doing that through modeling of things, they're already doing navigation systems. So if I can at least show them how the performance improvement changes what they're going to get in the end, or do I have to develop whole new mission capabilities and, whether that's magnav or detecting tunnels and bunkers or, whatever you're going to do, you have to connect the dots for them through to the mission, and it has to be one that they care about. And oftentimes that's the challenge, is in those conversations, either it can be difficult to get them to tell you what do I really care about, or the response I get sometimes is, I thought you were going to tell me. And it can be really difficult when now your job is to come up with the entire picture. It's like, yeah, I've got the sensor, I've got the system, I'm going to define for you the mission that matters to you, and you have to connect it all the way through to complete the motivation for the customer to say, yeah, that's what I want. And now, yes, your Quantum 2.0 system will succeed with me as a customer. That's a big ask.
Great, thanks. So I'm going to wrap it up here. If there's any questions from the audience, I think we have time for at least one. Or you want to ask one now? Go ahead. You got something about NQI, your initiative?
Actually, I have a question for Cami. In your various use cases, you didn't include biomedical, and I'm curious why that was.
So it's not an application that we are focusing on. Yes, so we are focusing on really the mining application, navigation, and object detection, but it's also something that can be done with this technology.
But Kathy, you are, right? On
Biomedical, yes, not specifically magnetometers, but to answer your question, I think the scale of what Cami is measuring versus a scale that you would measure in biomedical, which is probably at cell level, I think just how you would design the device itself would be very, very different. But yes, we are in the biomedical field, and we are working with academic partners who have the objective to deploy quantum sensing modalities for biomedical instrumentation, yes.
Great, thank you. So I'm going to go back to you, Kathy. So with the companies that presented today, do you see you could potentially partner with any of them?
Yeah, so who's using Photon here? So yes, anybody.
Yeah, Mike, could you partner with any of these companies?
Potentially. I don't, honestly, from this sort of summary, I don't necessarily know enough. I have a lot of questions, but yeah, I think true for everyone on stage and everyone here that this is about relationship building. And you've got to get to know people and their capabilities and their technologies really well before you can answer a question like, can I partner with you? But absolutely, there's potential across the stage and throughout the room from everyone.
So that's an important point. So you partner a lot, right? On
Yes.
Contracts, on projects.
Yes.
Maybe expand on that for a minute, so people in the audience know what you're talking about. Yeah.
Well, so we've got partnerships at university research levels with other, sort of the associated university labs, Georgia Tech Research Institute as an example, as well as small businesses that represent specific key component technologies. Just to name a couple, Freedom Photonics, Triad Technologies, making components that we like to use. And then we also look at partnerships on the application side. And so it's like, well, what platform will a given sensor go on? How will it enable a mission? And so whether that's a small business or a large business, we're looking for partnerships there. And it's all about creating a trusted relationship so that it becomes a true partnership. And when you can get to that point with a technical partner where it's essentially all part of the same team, and it's not a Northrop Grumman and then that other company, but rather we are doing this technology development, then you've created a partnership that can succeed.
All right, so you got your invitation if you want to partner with Mike. He's here all day today and tomorrow. Brent.
So probably main partnerships that we've had, number one at component level, that sometimes we are looking for developing new technologies at components. I mentioned that, just because they weren't available, a lot of times we've kind of done our own, but there are other areas that, like at the chip level that we just don't specialize in. So cases where you have robust technologies that you think would be useful for quantum sensing, very interested in talking to people. At more of a peer level, the US sponsors things called STTRs, Small Business Technology Transition Research, where they team universities together with companies. And so Air Force had something called the Quantum Collider a number of years back. And so we teamed with 4 different universities and different areas of quantum there. And then also, as I mentioned, if you're looking to eventually get quantum sensors into field of DoD systems, then you need to work with the prime contractors who are actually building the platforms, because you need to, the government doesn't necessarily dictate what goes onto the platforms. They're just getting a bid for, who's going to build the next a fighter jet. And you need to work with the people that are building the fighter jet in order to get the quantum sensing put onto those platforms. So it's kind of at different levels that we look at partnerships.
Great, thank you. Kemi, wrap it up.
Yeah, on my side, of course, absolutely. Partnerships are so interesting and also important. And as I previously said, this example of our partnership with this UK firm that's developing a gravimeter and co-integrating our solutions, both of our solutions, into a platform to bring value to end users. Of course, a lot like this, I want to highlight in this the support of NSC IRAP with Jean-Luc that helps us in this project. But yes, so on the component side, but of course also on complementing technologies that we cannot maybe even think of today, but can make a difference in the future.
Great, great. Thank you. Give everybody a round of applause.